Hi, welcome back. This is Professor Ridge, and today's lesson is on section 9.6, solving exponential and logarithmic equations. The principle of exponential equality. So if we have any real number b, where b is not -1, 0, or 1, b to the x is equal to b to the y is equivalent to x equals y. So basically we're saying that if we have an equation and we have written as the left side and the right side are written in exponential form and you have the same base, then the only way these expressions can be equal if the exponents are equal. So if the bases are the same and the expressions are equal, the only way that can happen is if the exponents are equal. So if I wanted to solve an equation, let's look at an example. About exercise 10. It says 2 to the 3x equals 64. So that the way I'm going to use this is if I can think of 64 as a power of 2, then I can drop the bases and say the exponents have to be equal to each other. So 2 times 2 is 4, times 2 is 8, times 2 is 16. Say 2, 4, 8, 16, 32, 64. So that's 2 to the 6. Now, invoking that principle of exponential equality, the only way these two expressions can be equal is if the exponents are equal. So 3x has to be 6. And then you're going to divide both sides by 3. So x must be 2. Okay, so that's one technique for solving exponential equations, is if you can get them to be with the same exponent. So let's try another one. I mean same base, sorry. So we have to write both sides with the same base. So 9x equals 27. So if you notice, 27 is not 9 to any power, so we can't do like we did on 10, but 9 and 27 are both powers of 3. 9 is 3 squared. 27 is 3 cubed. And here, if I do a power to power using exponent rules, that's you do 2 times x, which is just 2x. And now bases are the same, so we drop the bases, so that means the exponents have to be equal to each other. And then we're going to divide both sides by 2, so x equals 3/2. Okay, let's try one more. Number 16. So we got 2 to the x minus 1 equals 8. So let's see, 8 is the same thing as 2 to the 3rd power. So we can drop the bases. X minus 1 equals 3. Add 1 to both sides, so x equals 4. Okay, so pretty straightforward. Okay, so now the next principle is the principle of logarithmic equality. Okay, so for any log base a, and for x and y greater than 0, x equals y is equivalent to the log of x base a equals the log of y base a. Now remember, these are equivalent, so that means we can use this rule either direction. We can start with, if we have two logarithmic expressions that have the same base, then the numbers inside, the x and the y, have to be equal to each other. And if we have two numbers that are equal to each other, we can put them inside logarithms with the same base, and those expressions will be equal to each other. Okay, so again, we can use this in either direction. Alright, let's try an example. Alright, so if we look at exercise 18, we got 5 to the x plus 2 equals 15. Now, if we wanted to use our principle of exponential equality, we want to write both sides with the same base. And 15, we can't write that as a power of 5. 5 to the first 5, 5 squared is 25. So that's not going to work. There's not anything smaller that can write 5 where they have the same bases. So I'm going to use this principle of logarithmic equality. And again, my calculator, if it only has base 10 or base e, the natural log, I'm going to write these as numbers inside with log either base e, which is ln, or log, the common log, base 10. So that's what I'll do, the common log. Or I could have done ln, it doesn't matter, either one. And then, so once you've done that, then you're going to take the exponent and bring it out in front using the power rule. So we get x plus 2 times log 5 equals log 15. And what happens with this is a lot of people forget that the log of log 5 is just a number. And I can approximate it by punching it in my calculator. Let me turn my calculator on. So if I hit log 5 equals 0.6989700043, and again, log 5 is the exact number, but it's about 0.69. And so a lot of people get stuck here, and if I ask you, well, what would you do if I had this problem? X plus 2 times 7 equals 15, or let's say 38. Now I just made these numbers up. The x plus 2 obviously is the same as here, but the log 5 is a number, just like 7 is a number. Log 5 is not a very nice number. You know, it's 0.69897000043, and it goes on forever. It's an irrational number, but it's still a number. So if I had this problem, x plus 2 times 7 equals 38, what would you do? And if you said, oh, I would distribute the 7, and then I would subtract 14, so that's 24, and then I would divide by 7, so x is 24/7. And then I would say, yeah, exactly right, and that's exactly what you would do with this problem. Log of 5 is just a number, so we distribute it. So it's going to be x times log of 5, so that's like the 7x over in that sample problem, plus 2 times log of 5. And it's common that you write the number in front of log 5 so we don't confuse, you know, it's the log of 5 times 2. So but we write the 2 first, so it's 2 times log 5, and there's no confusion. Do you take the log of 5 first, then times it by 2, or do you do 5 times 2, then take the log? So there's no confusion when you do it that way. Hopefully that didn't confuse you. But anyway, so we're at the same step, like the 7x plus 14 equals 38. Well, this is the 7x plus 14 equals 38. Same idea. So my next step is I'm going to subtract the 2 log 5 from both sides. So we're going to get log of 15 minus 2 log of 5, which is x times log 5 equals that. And now to get the x by itself, you're going to divide both sides by log of 5. So my answer, exact answer, is log of 15 minus 2 log of 5 over log of 5. Now, what I could do if I wanted to, I could use my rules to make this one nice logarithm, but there's no need to do that. I can just leave it, punch this all in my calculator, and then see what my approximate is. So let's see. I'm going to go log of 15. Now again, you got to make sure you know your calculator. The calculator I'm using today, I punch it in exactly like it reads. So 2 times log 5. So the top is negative 0.221848, and the bottom, so I'm going to take that divided by log of 5, and that's going to get me about negative 0.317, and the book's asking you to round it to 3 places, but I'm going to say 4. 3.174. So the book had you just stop there, but it's typical you go 4 places with logarithms. So that's the approximate answer. This is over here, log 15 minus 2 log 5, all divided by log of 5 is the exact answer. Okay, let me show you one alternate way to do that same problem. You might like it a little bit better. Well, there's a couple different ways I can actually do it, but let me just show you this way. So let's from right here. So if I take log of both sides, bring the x plus 2 out in front. So we got the x plus 2 times log of 5 equals log of 15. Now instead of distributing the log of 5 like I did up there, let's just divide both sides by log of 5 right away. And you get x plus 2 equals log. Now be careful. We can't divide the numbers inside. 15 divided by 5 is 3. That will not give you the same answer. That is completely wrong. Okay, so don't do that. Just leave it separate like that. You can't combine that. You can't simplify it. That's the answer. Okay, so now to get the x by itself, you're going to subtract 2 from both sides. So you're going to get x equals log of 15 divided by log of 5 minus 2. And if you punch that in your calculator, you should get the same answer that we got above there. So let me try it just to verify that that is the same answer. Divided by log of 5. Okay, so that's 1.682, then minus the 2. And it's negative 0.31739, same answer. And you know, that might be a little easier for you to work out and kind of wrap your head around, and it's a little easier punching your calculator too. So you're welcome to do it either method, whichever way you like. Alright, let's try another one. Okay, so number 20, it's e to the t equals 20. And on this one, I'm going to, again, I can't make 20 with the base of e, but what I can do is do the principle of logarithmic equality and make these numbers inside 2 logs with the same base. But I'm going to choose ln this time, which should be a more natural choice. No pun intended, natural logarithm. The ln and e cancel each other and you just get the t. Using that property, if the bases, this is base e, this is base e, so they're like inverses, so they cancel each other. We get the t equals ln of 20. Punch that in your calculator, and you'll get about ln of 20 is 2.9957. Now, just like most things when we're solving, so let's look at 24, we want to get that object by itself. Like when we solved absolute value equations, you get the absolute value by itself first. When we solve radical equations, you get the radical part by itself first. Okay, so this is no different. We want to get the exponential part by itself, so we add the 65 to both sides. 7.2 to the x equals 65. Now we're going to apply our principle of logarithmic equality, and we're going to write this ln. I'm going to use ln this time. You can use whichever, ln or log. ln is 65. Now I'm going to bring the exponent out in front, so we got x ln 7.2. We're going to divide by, remember this is just a number, so just divide by it. ln is 7.2, ln is 7.2, so x equals, now that's the exact answer, ln is 65 over ln is 7.2, and then I punch this in my calculator, and we're going to round it to 4 places. Now, on my math lab, you do it to what it says. If it says 3 places, do it 3 places. If it says 5 places, do it to 5 places. It's pretty common to do logarithms to 4 places. I don't know why the book's asking for 3, but that's fine. 1, 1, 4, 6. And if you want to check, 7.2 to the 2.1146 minus 65, does that equal 0? So I'm going to go 7.2 to the 2.1146 minus 65, it equals, and I get 2.9 e to the negative 4, which is times 10 to the negative 4. Is that equal to 0? And the answer is, it's close. The idea is write 1, 2, 3, 4. And the reason it's off is because we rounded. Remember, it's not exact. So, yeah, that's the right answer. So I know it's off a little bit because I rounded. Okay, so let's look at 28. So again, we want to get the exponential all by itself, so subtract 4. So we get 5e to the negative x equals 5. We want to get rid of that 5 in front, so divide both sides by 5. So this was negative x equals 1. Now I'm going to do ln of both sides. Oops. ln e to the negative x equals ln of 1. And bring the negative x out in front, so we get negative x ln e, which is just 1, or I could think of the the rule that we did up there for 20. This is base e, this is base e, they cancel each other, we just get negative x. So either way, same thing. And ln of 1 is 0. So we're going to divide both sides by negative 1, so x equals 0. So that was an easy one. Alright, so now let's look at problems that start out with logarithms. So let me squeeze number 30 here. Log of x base 2 equals 6. Now for logarithm problems, okay, so for exponential problems we want to write it as the same base, and then we use the exponential equality principle. Or we make them numbers of logarithms inside, so we convert it to like a logarithm equation. With logarithm equations like number 30 here, our technique is we want to get the logarithm all by itself, one logarithm, and then convert it to exponential form. So convert to exponential form. So actually there's two things. If we can get the log with the same base on both sides, then we can drop the logs and then numbers inside are equal. If you get one log equals a number like this one, we want to convert it to exponential form. So remember, start with the base. Base is 2. Logarithm equals an exponent. So 6 is your exponent, equals x. And then in this case, solve it, but in this case nothing to solve, just simplify 2 to the 6 is 2, 4, 8, 16, 32, 64. And we're done. So pretty simple, that one. Let's try a little bit harder one. Number 34, ln of x equals 4. So this is a logarithmic equation again. So basically two techniques. I want to get a logarithm on one logarithm on each side of the equal sign with the same base, and then I just say the numbers inside are equal. Or get a logarithm equals a number and convert it to exponential form. So this is, you start with base e, logarithm equals an exponent. So 4 is my exponent. and the x is all by itself. And again, this is done. So x equals e to the fourth. And then I just punch that in my calculator and approximate it. So again, e to the fourth is the exact answer. But if I want to approximate it, hit my e button to the fourth power, 54.598. Two. It's 1.5, but rounds to 2. Let's try number 40. So I got Ln of 4x minus 2 equals 3. So I'm going to use that rule. I'm going to do e to the 3 equals 4x minus 2. I want to get x by itself. So add 2 to both sides. So e to the 3 plus 2 equals 4x. Then I'm going to divide both sides by 4. So I get, and I'll just flip it around, x equals e to the 3 plus 2 over 4. Again, that's the exact answer, but if I want to approximate it, punch this in my calculator, e to the 3, so e to the 3 plus 2, it equals, that's 22.0855, then divide that by 4, 5.5213. Oh, but I'll round to 4. Again, on my math lab, just if it says do 3 places, do 3 places, 4 places, 4 places, whatever the directions are. Okay, so again, I'm going to convert. You got 1 log equals a number, so I'm going to write it in exponential form. So 5 to the 3 equals 7 minus 2x. And then I want to get x by itself. Well, 5 to 3, that's just 125. So that's nice. Subtract 7. Now it's just a regular old linear equation. And then divide both sides by negative 2. So x equals negative 59. And pretty straightforward. Now, what happens if there's more than 1 log? It's like number 48. So we got log of x plus 9 plus log of x equals 1. Now, so what here we got to use our properties of logarithms to make this 1 log equals a number. So remember, if we're adding the logarithms like this, we can make it 1 log by multiplying the numbers inside. So we're going to get log of x squared plus 9x equals 1. And now we're going to, now we got 1 log equals a number, we convert it to exponential form, so 10 to the 1 equals x squared plus 9x. Now this is a quadratic equation, so now I got to go back, think chapter 5 or chapter 8, use quadratic formula, or I can get it equal to 0, which that's the way I'm going to do it. Get it equal to 0, factor it. Factor 10 and subtract the 9, or 10 and 1. Bigger one's positive. Signs are set each of those equal to 0. And then subtract 10, x equals negative 10, or add 1, add 1. Now we got a problem. With these, we always got to check back. If I plug this number, I should have done it in the other problems before. Remember that this number, when I plug it in to the original problem, the number inside the logarithm has to be a positive number. So if I check it, when I check it, you know, I have to think about domain of the original problem. If I put in negative 10 plus 9 plus log of negative 10 equals 1, in the original problem, this is not a real number. It's not defined. It's undefined. So you can't use it. So you got to throw that one out. When you put the 1 in, that's fine. You're going to get 10, log of 10 plus log of 1, which will be fine. Okay? So you gotta verify that you're allowed to use the number, that it's in the domain of the original problem. So you either check it just to make sure, do the complete check, or just plug it in and make sure that when you plug it in, it's going to be positive numbers. See, that's negative, no good. That one's negative. So it's no good twice, but even if it's no good for one of them, you got to throw it out. Alright, so just make sure you check that. Let's try another one of these. About number 53, we want to get both logarithms on one side and then make it one logarithm. So I'm going to subtract this log base 4 of x minus 5 from both sides. Now remember, when we subtract logarithms, we can divide them inside. And again, they have to have the same base. So that's the properties of logarithms. Excuse me. Okay, so now we got 1 log equals a number. We're going to write it in exponential form. 4 to the second equals x plus 3 over x minus 5. Now 4 squared is just 16. And we're going to multiply both sides by the LCD of x minus 5. So we got 16 times x minus 5 equals x plus 3. So again, I'd multiply both sides by x minus 5. Then I want to solve this. So let's see, distribute the 16. Is that 90 or 80? 80. And then I want to get the x's on one side. So it's just a regular linear equation right now. And I can add 80 to both sides. So that's 83. And then divide both sides by 15. So x equals 83 over 15. And I just need to check to make sure that when I plug it in that it's in the domain. So there's two ways. You can actually just check it or just think about the domain. So the domain is x plus 3 has to be greater than 0. So x has to be greater than negative 3 from the first one. That's from here. And then I'm going to check this one. And at the same time, x minus 5 has to be greater than 0. So x is greater than 5. So you pick the most restrictive one, which is this one. So we just have to check that 83/15 is inside this domain. So the domain is x has to be greater than 5. So 83 divided by 15, if that's more than 5, we're okay. If it's not, then you got to throw it out and this would have no solution. 83 divided by 15 is 5.53333, so that's fine. Alright, now the last type of problem, another technique we can do is, again, you want to get 1 log on both sides of the equation and nothing else, have the same base, and then we can just drop the bases and say the numbers inside are equal. So let's look at number 58. So I see there's 3 logs here, log of x plus 2 base 4 plus log of x minus 7 base 4 equals log of 10 base 4. And so what I can do is, if I can make this one logarithm, which I can, so we're going to multiply the numbers in. If you're adding the logarithms, you can multiply the numbers inside to make it 1 log. And now since I got 1 log on both sides, base 4, I can just drop the logs and the numbers inside have to be equal. Oh, I should have multiplied that out. So we get x squared minus 7x plus 2x is minus 5x minus 14 equals 10. Again, it's a quadratic equation, so get it equal to 0 and factor. So minus 24 equals 0. So it's x factors of 24 that subtract the 5. So it's at 8 and 3. And then set each of them equal to 0. So x equals 8. Or x equals negative 3. And again, I have to think about the domain. So, and I take the most restrictive one right here. So again, if I think of domain, x has to be greater than negative 2, and x has to be greater than 7. So these collapse to just this one, x is greater than 7. And I can see that x equals negative 3 is not in the domain, so I have to throw that one out, and I just get x equals 8, which is fine. That one is in the domain. So that one would be okay. And you could actually check it if you want to. Alright, so that concludes the lesson for 9.6. Go to My Math Lab, complete your exercises there, and I'll see you next time.